Hello everyone, my name is Dr. Nick Scroxton. I'm a paleoclimatologist at University College Dublin. I'm an Irish Research Council Marie Curie postdoctoral fellow. I'm currently investigating 20th century changes in southern African climate, including Madagascar. Previously, I was a postdoc at UMass, Amherst and MIT, working with Stephen Burns, Laurie Godfrey and David McGee, and there I was working on Pleistocene and Holocene climatic changes in Madagascar. And I've worked in both the northwest and southwest of the country. In their video, I think Vuari covered really well some of the basics of stalagmite carbon isotopes and their use for tracing past grassy biome extent in Madagascar, so I recommend listening to their talk first. I'm going to add a little bit more discussion on the advantages and limitations of using stalagmite carbon isotopes to track past changes in grassy biome extent. We'll start with some of the advantages. The main one is timing. So stalagmites use uranium-thorium dating, and these can often have errors of less than 1% and with no chance of bioturbation. And therefore, we can really build up some great chronologies using stalagmites. The second is that simultaneous to the carbon isotopes, we record oxygen isotopes, and these reveal what was happening to the climate simultaneous to any vegetative changes. And so we can use these two positive traits of stalagmites to help build event chronologies in Madagascar. The plot here shows details the chronology of vegetation and climate changes relative to fossil evidence of megafaunal change in northwest Madagascar. And this was from Godfrey et al. In 2019 in the Journal of Human Evolution. And it was built off stalagmite stable isotope data that I published back in 2017 in Quaternary Science Reviews. So we're going to focus on the lower panels. In green, we have the Speleothem delta 13C and a large positive isotope excursion, which indicates vegetation change from a C3 dominated environment to a C4 dominated environment. And then we can compare that to the stable oxygen isotope, and we see that that change in carbon appears to occur during a relatively wet period in the history of Madagascar, at least relatively wet for the last 2,000 years, as shown by a negative isotope excursion here in oxygen. And that both of these changes appear to occur either after or towards the end of the fastest period of megafaunal population turnover and population crash. So those are some of the advantages of what we can do with stalagmites, but there are some limitations and caveats. The first is that the carbon isotope signature is local, whereas the oxygen isotope signature is much more regional. So we're not integrating basin-wide changes, such as what you might get from sediment cores. Secondly, we struggle with proportional changes in C3 versus C4. So soil organic matter, leaf waxes, soil carbonates, all have linear relationships with the carbon isotope composition of vegetation. But this has not yet been proven for stalagmites, and in fact, the evidence so far says the opposite, that deep-rooting vegetation, so likely C3, dominates the carbon isotope signature of stalagmites, and therefore we may see threshold effects as we switch from one ecosystem to another. So what this means is that where we have large changes in stalagmites, which are say over 4 per mil, then we likely have an ecosystem change. But no one should be interpreting stalagmite delta 13C changes of 1 to 2 per mil as a proportional change in C3 versus C4. Further, as we have a threshold, we can't infer that C3 equals 100% total woodland coverage. Mixed biomes are likely to be recorded with a C3 isotopic signature coming from the deepest lying roots, which are likely from trees. And finally, like most delta 13C proxies, we're unable to distinguish between C4 and CAN vegetation, and therefore changes in southwest Madagascar may likely be missed by stalagmite records. Thank you everyone, and I look forward to talking with you at the end of the month.